Hey class, and welcome to part 6 on lighting. This time we'll be talking about windows. So in the last lecture, we went through daylight, providing daylight into windows. So let's look at the actual mechanics of the devices that add daylight, windows. Okay, going back to the very first lecture, electromagnetic spectrum. There is a band of the electromagnetic spectrum, which is visible to the naked eye. These are our colors. In the wavelengths from 700 nanometers to 400. Outside of that, it's invisible to us. Just because we can't see it doesn't mean it's not there. And the longer wavelengths we usually associate with heat being radiated off of warm objects. When it comes to windows, it's not completely transparent to all wavelengths. In fact, it has a very unique and specific shape in response to the electromagnetic spectrum. So when electromagnetic waves hit a pane of glass, just using kind of a typical profile of silica glass here, in wavelengths smaller than 200 nanometers, the glass basically reflects it off, kind of like a mirror, if you will. And that's a lot of the ultraviolet spectrum. We get a lot of transparency, 90% or so of wavelengths in the visible spectrum pass right through the glass, right? It's clear to us. We can see colors through it. It's great. Beyond that is the infrared spectrum. And windows can still transmit a lot of infrared wavelengths. But beyond, say, 5,000 nanometers, it once again reflects those infrared wavelengths like a mirror. And so this is how you get the greenhouse effect, right? Because the windows are functioning in a way like a one-way mirror, if you will, where you've got sunlight that comes in, it heats up the surfaces. The sun, being a very hot black body surface, emits wavelengths in the spectrum. And remember Wien's displacement law, where a wavelength is associated with the temperature of the object. Well, if the objects in our room are, say, computers, people, lights, plants that are relatively cool, say 70 degrees Fahrenheit to 100 degrees Fahrenheit, those are going to have very long wavelengths. And those wavelengths are going to hit the glass and bounce right back because it has no transmittance through the glass at those particular wavelengths. So what happens is the sun comes in, it warms up the surfaces, more sun keeps coming in, and sure, that sunlight could bounce right back out that window, but all of the long wave radiation that's occurring within the space of, people and computers that are slowly adding heat to the space, that just gets reflected back in, and you get this buildup effect or greenhouse effect, right? That's how greenhouses stay warm. Okay, so our goals for windows. Ideally, we don't have light coming through the windows. We can look out of them, and we have proper overhangs or blinds to basically keep sunlight from coming directly through the glass, but that's not always possible. And when it's not, we want to maximize the amount of visible light, our views, right? But block as much of that invisible radiation that's coming through and is adding a lot of heat to the space. In other words, our goals for windows are to maximize illumination and minimize heat gains. And that can be a tough thing to do. All right, on the first point, we want to transmit as much visible light as possible. There's a metric, it's called the visible light transmittance, or VLT. And this is listed on pretty much any pane of glass that you buy. If you go to Home Depot, it'll list it in a little sticker on there. And it's expressed as a percentage of the visible light that's going to be transmitted through the window. The maximum you're going to get is probably 90%. And anything above 70 to 80%, that's considered fairly clear. The lower it is, the less visible light is going to be transmitted. For example, I've got this sample piece of glass here. On the bottom are a whole bunch of numbers that list its properties, one of which being the visible light transmittance. I believe this is in the 0.3 range, and you can see it's a very dark blue tint on it. And that means that 30% of the visible light rays are allowed through this and 70% are blocked or reflected off of it. Okay, so that's step one, VLT. That's one metric to keep in mind. The next goal is to block ultraviolet and infrared light. We measure this in a metric called the solar heat gain coefficient. It's expressed as a decimal, and the higher the solar heat gain coefficient, the more solar heat gain you have through the window. In terms of code, generally you want your solar heat gain coefficient, SHGC, to be less than 0.4. And that means that only 40% of the heat gain coming from the sun is allowed through the window, and 60% is reflected back. I refer to code, let me get an example. I often talk about the IECC 2015 code, International Energy Conservation Code, because that's what has just been adopted by Idaho's commercial buildings. And if you're wondering, like, what is a good VLT or SHGC, I often look at the latest code for a good ballpark figure. If you see something that's worse than code, well, you can't install that in any new building. And if it's significantly higher than that, it's probably going to be expensive or cost prohibitive. So I like using the latest IECC code as a way of kind of gauging payback periods and reasonable figures if I'm doing an energy model or something like that for a building. So in terms of the latest energy code, we're looking at SHGCs that are less than 0.4, so blocking a majority of the possible heat. Because once again, going back to a typical profile of the glass transmission, yeah, we get some of this transmission in the visible wavelength. We want to maximize this. We don't need all this infrared heat to be passing through the glass, so we want to try and minimize that. And we can do that by adding films to the windows, coatings, sometimes doping the materials as the glass is being formed. So this green line here is an example of basically an uncoated, typical low iron glass window. This purple square here is our ideal. It's what we want to do. We want to have as high of a visible light transmittance as we can get, maximize the clarity of the window to our human eyes, while blocking the unnecessary invisible rays that add heat and energy to the building. So our ultraviolet spectrum, but especially our infrared spectrum. And the two kind of compete against each other. So it's impossible to get this perfect profile, but we can get close with some different coatings. This one has like a silver coating, it looks like, versus a triple silver coating. There are a range of chemicals out there, and you can get a sense of what the visible profile is going to be like in terms of transmittance across different wavelength spectrums. All right, so to wrap up, visible light transmittance, we want to maximize that, keep that above 0.7 if we can for nice clear windows, but reduce our solar heat gain coefficient quite as much. And just to give an example of that, let me pause really quick. All right, so what I have here is a little radiometer. I love these things. It's a very simple thing. It's basically a little vacuum, and inside, balanced on a pin, is a little pinwheel of these little squares, these little diamonds, and on one side is a black coating, which is going to absorb radiation, and on the other side is a silver foil coating, which is going to reflect radiation. And basically you add radiation source on one side, and it's going to cause this to spin. So if you put this in front of a window and the sunlight comes through, you'll see it start spinning a lot. I've got one of these hanging above my stove because I'm a nerd, and it's really fun to see it start spinning as soon as I start cooking, especially like on that electric coil. You know, it starts getting hot, eventually it starts glowing orange, and we know that's coming from the heat source getting hot enough to actually emit radiation in the visible spectrum. But even before the coil turns orange, this starts spinning, and you can feel and see with this radiation coming off of that. Okay, so I'm going to have two of these set up in front of a couple of halogen bulbs, which, once again, incandescent bulbs, remember that they emit a lot of heat and a lot of energy in the infrared spectrum, which isn't all that good for us, right? We want luminance, we don't want heat. We've got a typical double pane window here, and then I've got a window sample that has a low E coating or low emission coating. You can see the difference between these two. They're both fairly clear, so they've got probably very similar visible light transmittances. The coated one, the low emission or low transmissivity, if you will, has a slightly darker tint to it, but it still provides a pretty acceptable view. All right, and then behind I've got a couple of halogen bulbs, so let me turn those on. And you can see right away in front of the uncoated pane, a whole lot of radiation is being transmitted through, and I can feel that with my hand in terms of heat versus here, this low emission one is not transmitting as much heat, but you're still getting a decent amount of light through it, and that's really what we want. So pretty fun kind of hands-on demonstration of this lesson. Hope that helps you guys, and look forward to talking to you next time.